Okay, it's time to start the afternoon session. It's a real pleasure to introduce Beate Heinemann, who is the deputy spokesperson of Atlas. She's very busy. She's a professor in Berkeley, and she's been in essentially all the experiments or all the interesting accelerators in the last 20 or 25 years, DESI, Fermilab, I'm not sure about LEP, the LHC. So she will give us an update on the news from the LHC. Please.
Okay. All right. Thank you very much. It's a pleasure to tell you about the most recent LHC searches we've done. We had a major new release of results just in December, and so many of these results are rather fresh from the hot off the press. Just what I'll show you here on the picture are some of the highest mass events we've ever seen on colliders. So the high high mass dijet event with 7.9 TeV, nearly the full center of mass energy we had in run 1, and the dimuon event at nearly 2.5 TeV. I'll show you more about these searches. So just to summarize, so most of the results we've seen from the LHC so far were on run 1. On the right-hand side, you see, oh, maybe I have a pointer. Do I have a pointer? Yes, all right. So here you see the luminosity integrated in 2011 and 2012. The total data set was, summing this together, about 25 inverse femtobarons. And by now, Atlas and CMS have submitted nearly 1,000 papers based on these run 1 results. It's an incredibly rich data set, and we've used it, of course, to do, again, precision tests of the standard model. We've used it to discover a Higgs boson. And we've done many, many searches for new physics beyond the standard model. More than half the papers actually were searches beyond the standard model, which, as you could say, they were not successful. Of course, so we didn't find any physics beyond the standard model, but of course we were very happy to find the Higgs boson. So just to give you an idea, so this shows a summary of standard model measurements, the cross-sections of various processes, W and Z boson production, with jets, diboson production here, WWWZ. In all cases, you see the measurement that we did initially at 7 TeV with the 2011 data, and then at 8 TeV with the 2012 data. Then you see more and more rare processes. So you see that we're going here down by many orders of magnitude, going to rarer and rarer processes. And then the most, what really was a new era of measurement that opened up after having discovered the Higgs boson is also measuring the Higgs cross-sections and Higgs production channels. So we've looked at gluon-gluon fusion to Higgs vector boson fusion, various ways of producing the Higgs boson. And in all cases, the data agree with the standard model prediction. And we've done many, many searches for new physics. This is just illustrating a fraction of those. What's shown here on the left side for supersymmetry, and I'll come back to that later. This is the most theorists seem to favor supersymmetry over other theories. So this is looking, so we're looking more into that than into many other theories in more depth. So this is looking at many different particles and then the masses that we're excluding. So you see this is, for instance, here 1 TeV. So everything that's green is excluded. So you see that in many cases we're excluding particles below about a TeV, but not much beyond in supersymmetry, okay? And in some cases, it's only, the limits are only still 200 or 300 GeV. And then this is for many types of other exotic particles, for instance, leptoquarks, which are some sort of unified particle of leptons and quarks, heavy gauge bosons, W prime, Z prime, new gauge groups, excited fermions, et cetera, compositeness models. So you see we've been spanning a very broad range of models, and we've put many stringent limits, in some cases up to multi-TeV scale, in others, again, up to a TeV or half a TeV or so. Now, having looked at all these searches, so we didn't see any significant signal of new physics. I should also say that in order to fully test new physics as well as we were able to do, we were very thankful to this intense and fruitful collaboration with theorists who were often wondering, well, could you look at this also? What about this? And so on. So in the spirit of leaving no stone unturned in the data, this was very important to collaborate with theorists. Now, we did have a few excesses at the level of 2 to 3 sigma, and last year we started run 2, and this is one of the most interesting things in run 2 to follow up on these excesses in the data that we saw at the end of run 1. So one of them is, for instance, in CMS was looking for a lepton flavor violating decay of the Higgs boson to a muon and a tau, and they see a bit of an excess of about 2 sigma, and Atlas was, for instance, seeing an excess in high mass diboson production at an invariant mass of about 2 TeV. So I'll tell you more about this later. This doesn't work. Okay, so this is now what we did in run 1. Now, now we are in run 2. We have the first year of run 2 behind us. So what we did is now we have a higher collision energy. This is the single most important change. So it used to be 7 to 8 TeV in run 1, and now in run 2 we've started at an energy of 13 TeV. This was possible after a major campaign which took a long time, 1.5 years or so, to refurbish the magnet interconnects, which were not able to hold the current necessary to power the magnets to the level that is needed in order to achieve this energy, okay? Another thing is what's also changed is that we've increased the rate of collisions. So now instead of 20 million events per second, we now run at the design of 40 million events per second. There is a collision happening every 25 nanoseconds. And the increase in the center of mass energy dramatically increases the rate of processes, in particular at high mass. So this shows the ratio of the luminosity, the proton luminosity out of the protons for different initiated processes, gluon-gluon production, quark-gluon, and QQ bar production, as a function of the particle mass that you're producing. So for instance, a Z prime, say. And so you see that, for instance, at 1 TeV, well, okay, a Z prime, for instance, would be produced via QQ bar production. You see that this rate increases about a factor of 3. For the Higgs, which is primarily produced via glue-glue production, it's about a factor of 2.5. But then for processes here, for instance, for you could have supersymmetry particle production with a mass pair. If you have produced 2 particles of 1.5 TeV, this would be at 3, for instance. There you get very dramatic increases of more than a factor of 10 or even more. So and this opens up a new discovery potential, in particular in this high mass region, and in particular in strong production via gluon-gluon. Okay, so this is very interesting for us. So in total, in run 2, just to give you an idea, so for instance, the Higgs boson in the 4-lepton decay mode, in all of run 1, we had about 50 events. And in run 2, which is going to last the last year and then 3 more years, we expect to be more than a factor of 10 more. So just to get you an idea, there's so much more we can also do with those in terms of precision understanding. So run 2 started really on June 3rd, 2015. This shows pictures here of the control room. This is the control room of the Atlas experiment. This is the control room of the CMS experiment. And you just see many, many happy people who are very excited because what they see is these nice collisions here in the center of the detector. Since then, we've been collecting luminosity. So the luminosity is, by the way, given by this formula. It's just the revolution frequency, which is fixed, which is 11 kilohertz. So that's fixed basically by the ring size. Then the speed. The number of bunches, this in the LHC was 2,200 bunches last year. Then we have the number of protons per bunch, which is approximately 100 billion protons per bunch. And then there's also the area of the beam, how big the beam is. So the smaller the beam is, the higher the luminosity, the better for us in that sense. And you see here the integrated luminosity. So the red shows here 2015. So you see that we got about 4 inverse femtobarn delivered. And in the end, the good thing is that what you see, and this comes mainly to the end of my talk, what you can see is that it took a while until we really got going. We started here in June, but then it was a rather slow ramp up. The machine was new. It needed to be understood. This was not as easy as maybe one would have maybe hoped, but then it got really going end of August when some of the problems they were initially having were understood. And you see in the end we had a really good slope, a slope similar to 2012 where we got 20 inverse femtobarn. So we hope now in 2016 we will start and then rather quickly get to this slope. And then we will get of the order of 30 inverse femtobarn this year, 20 or 30, so something, again, as high as in 2012 or higher. Yeah, exactly. So we expect about 30 next year. Then what was also done in these 2 years of shutdown is that the detectors had undergone major improvements. So for instance, in Atlas, what we did is we inserted a fourth silicon pixel layer very close to the beam pipe. So before the most closest layer was at 5 centimeters from the collision point. This one is now at 3.5. So we can resolve better where the particles exactly come from. And then many other things, for instance, the muon coverage was improved, many repairs were done, etc. Overall, you see that, so this shows the fraction of channels available from each subsystem for CMS, for instance, and you can see, so the blue is run 2 and the red is run 1. So you see in many cases the blue is improved compared to the red, and basically for all of them, more than 97% of the channels are working now. There's one exception to it, which is the cryogenic system of the CMS magnet. There have been problems with it. So the CMS was lost approximately 1/4 of the data because it was not able to record it with the magnet. So meaning that you can't measure then the momentum of charged particles, which is critical for most of the physics programs. So this is being repaired during this shutdown, and there is good hope that this will be better than, this will fully work again this year. I'm just going to flash to you, it is a lot of work, just telling you as a theorist. So most of what we experimentalists do is try to study the performance of our detector. This is just showing a couple of plots here, but this takes a huge amount of time. One thing here, for instance, to understand how well we measure jets, just measuring the jet energy scale. So the ambition we have is to understand this at the level of a few percent, 2% or so. And in this case, it shows CMS has achieved this, Atlas has achieved this also. Efficiency measurements, we try to aim at understanding efficiencies at the sub-percent level so that none of these actually dominate our measurements, that ideally we're still statistically limited. We did, of course, greatly benefit from having done this already in run 1, but well, we needed to do it again in run 2. Okay, so let me just tell you then about some of the selected physics results we have obtained now at 13 TeV. So I'll first show you a few standard model measurements, but then I will primarily talk about the searches for new physics. So just to show that we know what we're doing before we're searching for new things, this shows a measurement, for instance, of the jet cross-section, a very beautiful measurement where we measure jet production at in different angular ranges. So this is the rapidity ranges. This is the different symbols, show different angular ranges as a function of jet PT, where we're now able to measure this up to jet PT values of 2 TeV. And then just for one example, so here for y less than 0.5, the most central jets, it's shown here as a ratio to the theory, and you can see how the data agree extremely well with the QCD prediction. Another example is that we then look for electroweak production of particles, W and Z bosons. So a W is selecting by looking for a lepton and missing transverse energy, or a Z boson we're selecting by looking for 2 leptons. And then we plot here, for instance, the missing transverse energy, which should correspond to the energy of the neutrino. In comparing data to the simulation, you see this excellent agreement between the data and the simulation. You see there is a little bit of background down here. So for W's, there's about 10% background. And then this is for Z's, where you actually see also a very nice agreement with the prediction, and here you don't see the background. The background is typically less than 1% for these processes. And so we measure the cross-section and compare this to the theoretical prediction. So this is at 1, and so you see all the data line up nicely around 1, indicating good agreement with the theoretical prediction. And this shows how these cross-sections increase as a function of center of mass energy. So this shows here our measurements at 7 and 8 TeV, and then the new measurements at 13 TeV. Similarly, we've also measured the top cross-section. So here, we can get actually very high purity top samples, just selecting 2 leptons and number of B jets. So once you have 1 or 2 B jets, it's basically completely dominated by top. And using some clever techniques, we are actually able to measure the cross sections here with a precision of a few percent also. Now I should say, so here actually, and this is for a long time during the running, we had an uncertainty of about 10% on the luminosity measurement, which was dominating the uncertainty of all measurements at the time. This has recently been improved. Atlas is now quoting 5% and CMS is quoting 4%. And this measurement will, I'm sure, will be updated soon with more precise luminosity measurement. This was also still using a small fraction of the data only. But we were already able to see that it roughly agrees with the prediction. So you see this was already in August when we made quite a few measurements here with this uncertainty of about 10%. And you see how the cross-section increased and also roughly agrees with the theoretical prediction. Okay, so then what was new in run 1 was the discovery of the Higgs boson. So a natural question is, well, do we see the Higgs boson in run 2? And so we looked. So in Atlas we looked. CMS actually hasn't looked yet. They're ready to look, but haven't actually looked yet. So the discovery channels in run 1 were the diphoton and the 4-lepton decay of the Higgs boson. And here I show you the run 2 plots. So this shows the diphoton mass spectrum. So we're looking for a bump here. So as you see, it's not, there is a few events, but it's not very significant yet. Similarly here in the 4-lepton decay, so the blue is the standard model expectation. You see there are a few events, but they could also be background. We don't know yet. So in other words, we are not yet conclusively observing the Higgs boson in run 2. So the cross sections that we measure are within 2 sigma. They are consistent also with 0, but they are also consistent with the theoretical expectation. When we combine these two, we measure about 24 with an uncertainty of about 20 compared to the prediction of 50. Okay, so we haven't really started doing standard model Higgs physics in run 2 yet with this data set. But we know that it's not a factor 10 bigger than it was before, for instance, and we can look, again, as a function of the center of mass energy, we can look at all these processes, all the standard model processes, and we see that the data always agree with the theoretical prediction. So this is just another view of this, as I showed you in the beginning. Now we're filling in this plot before I showed you for 7 and 8 TeV. Now we're starting to fill in this with the 13 TeV. So there you see nicely how the 13 TeV cross-section is larger always than the previous ones, and it again agrees with the theoretical prediction. So this is just showing the standard model measurements. So just to show you that indeed the standard model, so we are able to still do precision measurements, and they seem to agree with, within the precision that we have, they seem to agree with the prediction. So then now let's look for the unknown beyond the standard model, which is the main topic of my talk, actually. So there's, as I think many of you know, there's many good reasons to believe that there is as yet unknown new physics beyond the standard model. For instance, we know that there is dark matter and dark energy out there, and we don't understand its particle physics explanation. There is the matter-antimatter asymmetry, which may or may not be solved at the weak scale. There's the neutrino masses and mixing and many more. Oh, sorry, this is not first lecture. Forget this. And there's many, many possible new particles and theorists that have been invented by our very innovative theoretical community. So, for instance, supersymmetry that I already alluded to, but also many other particles, for instance, extra gauge groups. We could have extra dimensions, gravitons, for instance, decaying to 2 photons, which I'll talk more about. New fermions, like a B prime decaying to a B and a Z, etc., etc. So it's a very rich program of new physics to look for. And what is very interesting now at 13 TeV, that the cross-sections of many of these particles increase dramatically. So this shows the cross-section ratios for many different processes for many different processes. So for instance, W and Z boson production only increases by a factor 1.6 to 1.7. It's a QQ bar initiated process, and it is relatively low mass, so that's why it's not very much increased. Higgs production a little more. TTH production, so now we're getting to masses of about 500 GeV, 2 top quarks and a Higgs boson, so we're getting to like a factor of 4. But then much more dramatic, for instance, is gluinos. Gluinos is supersymmetric partners of the gluon. If they are 1.5 TeV, then we're getting a factor 50 increase. So even though we had about a factor 8 less luminosity at 13 TeV than at 8, we're now getting so big enhancements of a factor of 50 that we can already reach new physics beyond run 1. So then also quantum black holes, there you can, if they are massive, you can get nearly infinite cross sections, so you can get enhancement of factor 10,000 or so. So let's talk a little first about supersymmetry. So I hope I don't bore you too much to remind you of the motivation of supersymmetry. So it's very well motivated because it has 3 very appealing characteristics. One is that it can solve the so-called fine-tuning or hierarchy problem. So that is within the standard model, the Higgs mass is unstable, and this comes primarily due to the fact that there are quantum corrections to the Higgs mass due to the top quark loop. That's this loop here, which is has a very large value. And supersymmetry naturally stabilizes it by having stop quarks. And this has then a negative sign, and so this whole thing sort of cancels, and so you get a stable Higgs mass near the weak scale. Then this only works if the stop quark is light enough, and this is a bit of a question of taste, how light you want it to be. That depends on how good do you want the cancellation to be. This is rather subjective, but let's say everyone agrees the lighter the better. Okay? So they need to be sort of near the weak scale in order to be able to really solve the hierarchy problem. Another thing is that the lightest supersymmetric particles is a very good candidate for dark matter, and also in supersymmetry one can achieve the unification of forces. Now, from an experimental point of view, the really good thing also about supersymmetry is this large increase in cross-sections in run 2. So this is shown here. So for instance, here the cyan shows for gluino plus quark production, so the inclusive production, and you see here at 1.5 TeV this large factor of 50 that I was already alluding to. For other particles, for instance, stop quarks, which are very interesting, which are arguably the most interesting supersymmetric particle for our purposes at the weak scale, the increase is not quite as large. So first of all, we expect them to be lower mass in order for us also to be able to probe them and for them to play this role. And then we get factors of 30 or so increase. So the increase is not quite as dramatic. Okay. So just because I don't know which background exactly you have, I think many of you know this. So this is basically what supersymmetry does for all standard particles. You get a supersymmetric particle, so you get quarks and leptons, and then you get the gauginos here. And these mix into so-called neutralinos, which are neutrally charged, and charginos, which are charged. Yeah, and then supersymmetry, depending on, we already know that it's a broken symmetry, otherwise we would have found it. So we would have the same masses as the standard model particles. And so depending on exactly how it's broken, the phenomenology changes. So it's not feasible for us to interpret our data in all models than there are, depending on how it's broken and so on. So we use simplified, so-called simplified models, where we assume any signature is dominated by 1 or 2 or 3 SUSY particles, and we interpret in terms of the masses of those particles. Actually, I have more on this. So this, in principle, a lot of things can happen in supersymmetry. So one thing that can happen is that if you produce 2 gluinos, that regardless of what the masses of the squarks are, even if they're heavy through a virtual exchange, you can end up with 4 quarks and 2 neutralinos. So our signature in the detector is then when we have 4 jets and something missing. Okay. Now, if you, for instance, have squarks, you can have 2 quarks and 2 neutralinos. So then we have 2 jets and something missing. But there can be more complicated things, that you could have an intermittent particle in chargino, for instance, and then you have also W's, and these again decay to quarks, and you have 6 jets plus missing ET, okay? And you can come up with more and more complicated things. And so our analyses are actually very rich. So we are looking at all these jet multiplicities. We are also scanning the range between missing ET, which is really the transverse momentum carried away mostly by these neutralinos, and the sum and the jet activity, which we normally call HT, which is just the sum of the PT of all the quarks. Okay, so these are the 2 dimensions that characterize the hardness of the events, and they are related to the masses of these initial particles that get produced. Sometimes we sum all of the transverse momenta up, then we call it M effective. I'll show you in a few plots. And then, as I said, the hierarchy problem is really one of the big things why we think that there should be new physics at this scale probed by the LHC. So we have a lot of searches that target in particular B quarks. And this is, so we have, since B hadrons have a lifetime, we're able to discriminate B quarks from other quarks quite well. And so our strategy is to look for many signatures and to interpret both in simplified models and in a particular model called M-SUGRA. In any real model, many of these signatures can appear at the same time, but it's very model dependent in how exactly, etc. So we just look at a very broad number and interpret them. So this is maybe the most powerful search. It's just a really inclusive search for jets, many jets, and large missing transverse energy. So here I'm showing you, so what we do is we just say we don't want there to be any leptons. So this is targeting somewhat these kinds of events, yeah? So we want there to be no leptons, we want there to be large missing energy, and then we look at actually 7 different signal regions depending on the number of jets. And this is an example, for instance, for 4 jets. So I'm going to show you quite a few plots of similar type, so I'm going to go through this one a little slower. So the data are shown here as the black points. Then you see the different background contributions as the colored histograms. So for instance, W plus jets is a major background, and TT bar production. Because even though they have a lepton, sometimes we miss the lepton, and so they enter this. But then, so this is where it's background dominated, but then here in the tail, this is where we're sensitive to signal. And so this dashed purple histogram, this shows the signal we would get for a gluino pair production signal of 1.4 TeV in mass, okay? So this we would be able to see with this analysis, and if we make a cut here where the arrow is at 2.25 TeV. And exactly where we place the cut depends on the jet multiplicity and so on. And so in total, we look at 7 signal regions, as I say, and they have these labels here, 2-jet, 4-jet, 5-jet, 6-jet regions. And then you see here the data compared to the background expectation. Here you see the ratio. So as you can see that in all of these 7 regions, the data agree with the background expectation. And so we haven't found SUSY in this analysis. Similarly, we do then analyses. For instance, when there's W's, we can get leptons in the final state. So we look at events where we have 1 lepton plus jets plus missing ET. And this shows here some similar distribution. Unfortunately, it got cut off. Here, the label. So again, the SUSY signal you would see here is this red histogram. And the data you see, they agree with the background expectation. In fact, in this analysis, one expects a boost. So we search for events. We sometimes do that. Basically, these quarks can be very close together, and then you get a very high, very energetic jet. Or the W, if it's very energetic, it just appears as one fat jet, and we look at the total jet mass of those. This is shown here. So this total jet mass versus the transverse mass in the event, and we expect the signal here to have high values in both, while the background is primarily in this low region. Oh, by the way, I tried to be very good at putting references everywhere. I think sometimes I might have not put it because I might have run out of time, but most of the time I've tried to put references here. These are all preliminary results at this stage. Yeah. Okay, so having then not observed particles in our any excess in our search, we place limits on SUSY particles, and this shows examples. So this shows, unfortunately I cut it off. So this shows also the gluino mass. Here the gluino mass, in all cases the gluino, here the gluino mass is on the x-axis, and the dark matter candidate, so the neutralino mass is on the y-axis. And so everything beyond this fat red line is excluded by the run-2 data. So you see that we're excluding basically up to 1.5 TeV gluino mass here, as long as the neutralino mass is below about 700 GeV. And then in blue, you see what we did in run 1. Okay? So we were able to probe gluinos, in this case, beyond run 1, not far though, like about 100 GeV or a bit more in some regions, okay? Similarly, this is here for squarks. So again, we gained approximately 100 GeV in the squark mass. And we were, yeah, so we were able to exclude now squarks up to about 1 TeV. And then this is another example. So this is now an example where the gluinos decay via B quarks rather than ordinary quarks. So it decays via B quarks here. And this is an example that is actually CMS has many alternative analyses that are all trying to have the highest sensitivity. And you see that here up to 1.6 TeV or so is excluded in the gluino mass based on one of their analyses. Okay. Now, let me talk a little more about naturalness, because this is the thing that people pay most attention to in the supersymmetry gain. So basically, naturalness dictates that the SUSY spectrum should be approximately like this. We have a gluino here. Below, at lower masses, we have stop quarks, and then the lightest particles are these charginos and neutralinos. And so the stops, bottoms, and gluinos should all not be too heavy. And this is why we're making a large effort to target the 3rd generation in particular in our searches. So this shows one of these searches, which is for same sign leptons. So what we're looking for is either spottom quark production or gluino production. And because you get many W's, you get W's from each of the tops, and you get sometimes W's by themselves. And these W's decay leptonically, and then we get sometimes leptons of the same charge. Now, the interesting thing about this is that in the standard model, this doesn't happen very often, that you get 2 leptons from the same charge. And so there's rather a little background, in particular if we also look for B jets. And so this we do here. So this shows, for instance, the missing ET distribution for one example in these events. So you see the background is rather small. There's only five events in the background, and we observe 7 events. Consistent again with the background. And again, here we have actually many different signal regions that we're looking for. And you see here the data just compared to the background expectation. You see that they actually agree with the background expectation everywhere. And we have many searches with B-jets targeting this, and this shows some more examples. The missing ET distribution. Here we have 2 events, and here you see the background estimate and the hypothetical signal. Again, the data are consistent with the background. Similarly here for events which have 3 jets. So we've already looked at a lot of final states and in a lot of detail. But we haven't seen anything there. And so in this case, where we have gluinos decaying via top quarks, we again place limits on the gluinos of up to 1.6 TeV on the gluino mass in this range. And there's, again, you see here CMS having many analyses targeting this because this is so interesting, such an interesting channel. And in run 1, we had a limit of about 1.4 TeV, which you see here in gray. So we're already probing quite a lot beyond run 1. Now, let's come to then the things where we had excesses in run 1. And one of them was in opposite sign leptons and jets. So basically looking at signatures like this, where we have a Z boson, decaying into leptons either on shell or off shell. And so the interesting thing was that unfortunately both Atlas and CMS saw a bit of an excess, but in different ways. So CMS was looking at this dilepton mass in events with many jets and missing ET at the dilepton mass, and what it saw is, so here below, so this is here, this red this peak here, this is due to the Z mass. And then CMS saw that the data was, there was a so-called edge, that there were more events here in this tail compared to the background expectation. So the background expectation would have predicted this black line, and what was observed was this blue, okay? So there were a few more events. On the other hand, what Atlas saw more events in the Z mass window than they were expecting. So the expectation here is again in these colored histograms. So you see, so this is basically like 1 event per bin or something, but Atlas saw quite a few more. So this is just in the electron channel. So basically Atlas saw a 3 sigma excess in on-shell Z production, and CMS didn't see anything. And Atlas saw nothing in off-shell production, and CMS saw 2.4 sigma excess. Okay. So the conclusion, the primary conclusion was that, well, anyway, of course, none of these are particularly significant, but with run 2 data, it's interesting to see what we see there. So both experiments had a look. So CMS did both the on-shell and off-shell search already. This is the off-shell search. What's shown here is, again, the dilepton mass distribution. And so this red dashed line is what one would have expected based on the run 1 axis, but the data don't support this. The data are perfectly consistent with the background estimate alone. So CMS does not see this axis that they saw in run 1. CMS also did an on-shell search, and in that one would have expected, so here at high missing ET, there an axis to be showing up. This is where Atlas had one, and they don't see anything there. The data are perfectly consistent with the background estimate. However, then Atlas has done the on-shell analysis so far, and Atlas does see a little bit of an excess. It sees 21 events observed compared to 10 expected. The significance of this is only 2.2 sigma, and this is what the data show like. So I would say it doesn't look all that convincing that there is any significant new physics there, but we can't completely close this issue yet. We need to see what's happening with Atlas and CMS and whether they become consistent during the course of run 2. So with more data, and also with maybe further analysis of the current data, hopefully there will be more news on this. Then something else we can do is look for the Higgs boson. I told you, so in run 2, we are not yet very sensitive to seeing the standard model Higgs boson yet, because the cross-section increase isn't as dramatic and we didn't have that much luminosity. But in the MSM Higgs, in the supersymmetry, the Higgs boson rates, there are more Higgs bosons, first of all. So normally we have 2 Higgs fields there, and which result in 5 physical Higgs bosons, out of which one of them has a mass of 125, the other ones we don't know. And the cross-section can be significantly enhanced. So this shows the cross-section times branching ratio, so it can be enhanced by this factor of tan beta squared, which is the ratio of the 2 vacuum expectation values. And if tan beta is high, we also expect this to decay into 2 taus. And so we can look at this. So this is the first search we've done here. So we basically look for taus decaying either leptonically or hadronically. And then we place also cuts on the angular separation and so on. And then we form a mass type quantity, which I show you here. So for both, so this is we form a transverse mass between the tau and missing ET, and we basically sum those up, and we call this empty tot. And this is shown here. So this gives discrimination again between the background here as the colored histogram, and this purple open histogram is the hypothetical Higgs boson at 500 GeV. So you see that there is discrimination there, and we can use this to search for such Higgs bosons. And we've done that. And as you can see here, the data agree with the background expectation. And so we place limits then on this quantity tan beta versus the mass of the Higgs boson. So you see, for instance, at 1 TeV, we are now able to exclude tan beta values of 45. And this is also slightly better than run 1. Run 1 is shown in red, so there we were able to exclude something like 55. So it's slightly improved here. It is improved here in the high mass range. In the low mass range, the run 1 limits are actually still more stringent. Okay, so that was it with supersymmetry. So let me tell you about non-SUSY searches. So first of all, a very classic search, very beautiful and classic search is the search for W primes. So W primes can, for instance, decay into a lepton and a neutrino. And so via diagrams like this. And so we look at the transverse mass of this lepton and the neutrino, and you see in black, you see the data points, again, compared to the background expectation. These green, blue, and red things here, these illustrate how a W prime signal would look like. So you see the hardening of the spectrum, and you see the data agree with the background. And we are actually placing limits of about 4 TeV now on W prime bosons decaying leptonically. Alternatively, W primes, for instance, it could be a right-handed W, for all we know, rather than our left-handed standard model one. And then it could decay to quarks, to top and B, while it might not decay into leptons at all, because it might only exist in a right-handed way. So we're looking for that also. And so you see here we're forming a mass type quantity, the invariant mass of the top and the B quark. And you see here some hypothetical signals. You see the background expectation and the data show no hint of any W prime. And so we place limits of about 2.5 TeV. Similarly, we can also look for high mass dileptons. Z prime can produce those, or also a graviton, for instance. And you see here the dilepton mass. So you see here the Z peak and 90 GeV, and then this is the main background is Drarian production of dileptons here in blue. And this is how a signal would look like. And here they see the same here this is for electrons, this is for muons, this is CMS, and this is Atlas. I've kind of mixed, I put at random a little bit chosen whether I show you Atlas and CMS. In many cases, both experiments have them, and it's just a bit, I didn't want to show you all plots twice because it's a bit boring. I would do that for a discovery, of course. So, Oh, this is not 2 channel, this is a typo. So the highest mass dielectron event is here at 2.8 TeV. So this actually came in CMS very early during run 2 and caused a lot of excitement, but then it doesn't have yet any other cousins that it found. So the limits are approximately 3 TeV. Similarly, we can look for dijets. So now we're looking for, again, resonances decaying to quarks or gluons. So for instance, we could have excited quarks, we could have W primes, et cetera, et cetera. So it's a very model independent search. So we were just looking at the spectrum and we're looking for bumps on top of this spectrum, bumps corresponding to the detector resolution, consistent with the detector resolution, and I'm showing you here an example of those. And so we don't see any, and we place limits on many of these scenarios. Again, here we're probing now, we have dijet mass spectra up to more than 6 TeV, and we're probing, for instance, excited quarks up to about 5.5 TeV. All right. So then let me tell you, come to another di-object search, which is diphotons. So diphoton resonances are also predicted by theories beyond the standard model. For instance, one could have extended Higgs bosons where diphotons are produced again in a loop, in the decay of the Higgs boson through a loop, similarly to the standard model Higgs boson going to 2 photons. And it's always just like with dielectrons, photons we measure with very high precision. So it's very nice to look for a narrow resonance there. There's also graviton models with a spin 2 graviton decaying to 2 photons, where the parameters, I'm just going to introduce a typical parameter that defines the coupling is here kappa tilde, which is related to the Planck mass. And experimentally, this is important because the width of the resonance is related to approximately 1.4 times kappa tilde squared. Okay, so there's new analyses from Atlas and CMS, and they're slightly different. Atlas has really focused on searching for scalars, and the cuts they've placed are given here. So it has PT cuts on the 2 photons, which are related to the mass. So the higher mass object, the higher the PT cut. This is inspired, in fact, by the standard model Higgs search where this is done. But what it does, it causes the photons to be primarily in the central region of the detector, in the barrel region of the detector. CMS has focused its analysis primarily on gravitons, and it has more simple cuts. It just requires 2 photons with a PT greater than 75 GeV. And then it has 2 categories, one where both photons are in the barrel, and one where one photon is in the end cap and the other one is in the barrel. The background to the search is 80% true diphoton events, more than 80%. So basically in the barrel end cap of CMS it's about 80%, in barrel it's about 90%, and in Atlas it's about 90–95%. So it's very pure QCD diphoton production. Now here, just as with the dijet search, what we do is we just parameterize the background as a smooth function, and we're looking for a peak on top of that. This was also what was done for the Higgs discovery. And so the functions that we use, I show you here. So this is the function that Atlas is using. It scales here, oh, this should be photons. It scales with the photon mass and divide by root S. And this is the function that CMS is using. And in order to test that these functions work very well, they are tested on next to leading order QCD and on Monte Carlos to make sure that they have the flexibility needed and they don't introduce any artifacts. And as I said, the background is primarily diphoton events, which we understand quite well. And so this shows the diphoton mass spectrum. On the left, I show you the CMS spectra. This is barrel-barrel, and this is barrel-end-cap. And it shows you the Atlas spectrum. So what you see is, and this has caused a little bit of excitement in the past 2 months, is that Atlas sees a bit of an excess here in this region near 750 GeV. This shows here the spectrum itself, and this shows the data minus the background. And as I say, this background is using the smooth functional form that I described before. And then in CMS, If you look closely, so you see also at 750, which is approximately here, you see also a little bit of an excess here in the barrel events, while in the end cap, I would say you don't really see anything. And so what we do is to estimate what is the probability that the background fluctuation would cause a bump as big as the one that we observe or bigger, okay? And this is done here for CMS, and this is for Atlas. So these probability plots, basically they have then these deep peaks. So as you can see, the probability value of CMS, the lowest one, is at about 760 GeV, and it corresponds to like 6 times 10 to the minus 3. This corresponds to about 2.6 sigma. And Atlas is something slightly deeper, so it goes nearly down to a probability of 10 to the minus 4, 2 times 10 to the minus 4. This corresponds to 3.6 sigma at 750 GeV. And it can be slightly increased if we allow for a larger width. Now, having said that, so this sounds all quite exciting. However, we of course have to consider the fact that we're scanning this whole mass spectrum. So we need to consider how probable is it that we find a fluctuation at least as large as this one anywhere in the mass spectrum. And if we take that into account, we're basically getting down to a level of 2 sigma in Atlas and like 1 sigma in CMS, okay? So this is not conclusive. Apart from that, I would conclude that we need the 2016 data to draw any conclusion on this. Now, your theoretical colleagues have been extremely busy with this, so this is what I call the theorist frenzy. So these preliminary results were released on December 15th, and now 6 weeks later, there's already 192 papers on this. All right. Well, I invite you to study the literature. I don't have enough time to read all these papers. Anyway, so there are, of course, constructive suggestions, actually, that we could also look. If there is a diphoton thing, there could also be a gamma Z or a ZZ, so we're supposed to look at other diboson for other diboson resonances and so on. So there's a lot of useful suggestions. All right, so talking about dibosons. So another axis that I alluded to in the beginning of the talk was that of diboson resonances. So Atlas saw in particular this bump here at 2 TeV. In the search for WW, WZ, or ZZ resonances. Actually, the combined significance, so once you have Ws or Zs being produced, these can either decay hadronically or they can decay leptonically. And so we're looking at many different signatures of those, and then combining all of those, you see actually what you saw here, this red, this shows that peak, okay? This shows from the all hadronic search where both decay hadronically, or the other ones didn't really see anything in the same mass range. These are the different colors, but when you combine the whole thing, you get 2.5 sigma, okay? And CMS, interestingly enough, also saw some sort of, here you see these bumps, these are where the limit that they set was weaker than what they expected to set in the range at around 1.8 TeV or so. So this also, there's quite a few papers. I don't think 192 papers, but quite a few papers were published on this. So we also looked at that right away in run 2. So what we do is, so we use many of the leptonic and hadronic decay modes. The hadronic Ws and Zs, and this has become a very much used technique now in run 2, is because of this large boost, they just appear as one fat jet, and then we look at the properties of that jet to resolve whether it's really one jet or it's basically two quarks having overlapped each other. And so, so this shows, for instance, when we look at the jet mass after a cleanup technique called pruning, and so you see the QCD production, you get this gray histogram, while if you have a W or a Z, you get like some mass there which is consistent with a W or Z. So this is the techniques we're using. And there's other so-called substructure variables we use, which have some discriminatory power between QCD jets and jets from W and Z bosons. And there's also angular variables. So this just shows the difference in rapidity between the W and Z boson candidate. And you see that for W prime at 1.5 TeV, these are kind of close to each other, while for QCD events, these are further apart. And so this is a lot of analysis, actually, and this is just illustrating that. So we're looking basically for peaks in many, many of these distributions. So this shows the one where Atlas saw the excess in 1,1. So near 2 TeV, you see there's 3 events, but there's also about 3 background events. So it's a bit inconclusive. We basically don't quite have enough data yet to resolve the situation. But what we see is that nowhere do we see a significant signal at this stage. But we are not able to exclude the run 1 anomalies yet. So the data is consistent with background, but again, we need the 2016 data to conclusively probe the run 1 excess. Last but not least, let me tell you briefly about black holes, because I understand some of you are studying quantum gravity or trying to study that. Now, we do look for it. Of course, we need to be extremely lucky for this. So we're looking for microscopic black holes that evaporate via Hawking radiation. And so then they evaporate quite democratically. And one of the best ways to look for it is just to look for many objects at high energy. And so that's what we do. Basically, we're looking for multi-jet event where, in fact, we let every particle is a jet. Like a photon is for us a jet, then electron is a jet. We just don't care. We just take any particle, any high-energy calorimeter deposit is a jet, basically. And then we just sum up all of these, and we require this to be above 1 TeV, and then we look at many multiplicities. So this shows, for instance, here the HT distribution for 3 jet events or for 6 jet events. And so the background is falling, while the signal we expect here to be at high HT values. And as you can see, that there is actually, so the blue line indicates here where we start to search for the signal region. So here above 3.7 TeV, and you see that there is no data events, unfortunately, in our search region. And so we set limits in such models. Okay, so let me then conclude. So LHC provided about 4 inverse femtobarns of data in 2016, and I hope I could show you that the LHC machine has really been working very well, in particular towards the end of the run, where it will pick up later this year in about 2 months. And the Atlas and CMS detectors are also working very well. We've actually managed to release about 40 results of searches for new physics, even only 6 weeks after data taking finished. That alone indicates how well the detector is working. This is highly non-trivial, in fact. And we've also produced many measurements. I didn't highlight them so much, but the ones that I showed, I mean, as you saw, so all the measurements so far agree with the SAR model prediction. We haven't seen any significant excess in any search, but we have a few things which are at the level of 2 sigma, and it'll be very interesting to see what we see in the 2016 data, where we expect 30 inverse femtobarns. So my conclusion is that 2016 should be another exciting year for LHC searches for new physics. Thank you. Well, so I'm not sure we will combine them. So far, these are only preliminary results. So obviously, both experiments are now working on finalizing the analysis to publish it in the first place. And so I think after that, we will see, but I'm not sure. Because the thing is that these combinations are really quite hard. And already by summer, we should have more than doubled the current data set, so it's not obvious that that's the right thing, that we should just combine, or maybe, I mean, because we will soon get more data, and this will tell us much, much more than any combination will.
I have a question.
Yes.
What is the improvement on the measurement of the top quark mass in the run 2?
Oh, this is difficult. This I don't know. So the top quark mass precision is completely dominated by our theoretical understanding. And normally, having higher energy is not necessarily better because you get more gluon-gluon production, you get more radiation. So having more radiation so makes it harder to control it. So I'm not sure even that in run 2 we should get a better result than in run 1. I don't know. I can't tell you.
There are many people talking about the beta stability of the standard model, or even inflation that depends precisely on
Yes. But there, I mean, so we still haven't seen the final results from run 1 for the top mass. So in Atlas, we're still working on that analysis, and this is really hard work. So yeah, so I don't know yet in run 2.
But we are desperate.
Yes, I understand. Yes?
So when you talk about the graviton, you mean the standard graviton of general relativity?
Sorry?
You mean the standard graviton of general relativity?
Yeah, but it needs to be in a theory of extra dimensions. So we need to have now so we need to now have extra dimensions at the weak scale, so so it's basically like in Randall-Sundrum models, for instance, that you have a graviton resonance at 2 TeV, 3 TeV decaying. Sorry?
Maybe it's a massive singularity, because mass singularity cannot.
Yeah.
Kaluza-Klein resonances.
Yeah, Kaluza-Klein resonances, right.
Yes, Alex.
Yes, you showed these two functions you used in CMS and Atlas to fit the photon-photon background.
Yes.
They look very different from each other. Can you perhaps expand a bit on that?
Yeah, so I can't exactly explain. So the Atlas, I can't really tell you why CMS chose this one, to be honest, but Atlas chose this one. So this is inspired, in fact, by the Dijet mass search. The Dijet mass search has used this function for more than a decade. Already at the Tevatron, this was the function used. And so this inspired now the photon one. I don't know how CMS chose this one. I don't think it's described in their paper. I think naturally we will try each other's functions and try to see, or at least in the systematic uncertainties, take into account what happens. Of course, we change the fit functions when we estimate the systematic uncertainties, but I'm not sure now whether we've ever tried this function. They are mostly inspired really by using next to leading order QCD Monte Carlo and then seeing what fits.
Okay, well, let's thank Beate again for a very nice presentation.